Can too much precision lead to the wrong answer? That's the paradoxical truth behind the uncertainty of certainty, where highly precise data can actually be less reliable than more modest measurements. In science and engineering, we often associate greater precision with greater truth, but when models are too finely tuned, or when instruments measure beyond their stable limits, the results can become deceptively confident and dangerously misleading. Overfitting, in particular, is a key culprit. When a model is forced to match every tiny fluctuation in data, it may memorize noise instead of learning patterns, losing its ability to generalize. So how does precision turn into a trap? Every instrument has its threshold. Go beyond it, and you begin to record artifacts, not reality. Similarly, when datasets are overanalyzed, researchers may detect patterns that aren't truly there simply because the model is too flexible or the data too clean. This illusion of certainty can lead to false discoveries, fragile predictions, and overconfident conclusions. It's a reminder that in both measurement and modeling, true accuracy often requires embracing uncertainty. In the end, the quest for perfection can backfire because the sharpest picture may be the one that's most carefully filtered, not the one that's most real. How can data that glitters with extra decimal places betray you more than a rough estimate? In today's world of ultra-sensitive sensors and machine learning algorithms, precision often means mountains of digits. And yet, the more precise the measurement, the greater the danger of being misled. What happens when you pour every bit of noise into a model? That's overfitting. Your algorithm becomes a virtuoso at memorizing random fluctuations in training data, mistaking them for real patterns. When you show it new data, it stumbles because it learned the quirks of noise rather than the underlying truth. In effect, you traded generality for phantom precision. Your model looks flawless on paper, but fails in the real world. Can your instruments lie too? Absolutely. Every sensor has a finite accuracy bound by calibration, temperature drift, and electronic jitter. You might read microns on a laser interferometer, but if the device warps with heat or its reference mirror shifts with humidity, those extra digits become a confidence trick. In practice, resolution, the smallest change you can detect, outstrips accuracy, how close you are to the real value, and blind trust in resolution alone leads you into a false sense of certainty. So how do we navigate this paradox? Question your precision. When you see 0.00012345, ask, do I really know all those digits, or am I chasing sensor ghosts? Simplify models, favor robust trends over convoluted fits. Sometimes a straight line beats a 10-parameter curve. Validate independently, cross-check with a different method or instrument. If two approaches disagree, it's a clue that at least one boasts spurious precision. In the end, the greatest lesson of the uncertainty of certainty is that precision without reliability is a mirage. True confidence comes not from counting decimals, but from understanding your limitations and designing measurements and models that stand up to reality. The uncertainty of certainty paradox highlights that data with extremely fine precision, many decimal places or high-resolution readings can be misleading if they arise from overfitted models or reach beyond the instrument's true capability. Such false precision gives a veneer of confidence while masking underlying errors, noise, or unmodeled effects. Consequently, the most detailed dataset is often the least trustworthy unless its limits are rigorously understood and validated. A machine learning model fit to historical sales data may report 99.9% accuracy on the training set, but collapse when presented with new market conditions. It is like owning a high magnification monocle that shows every speck of dust, yet overlooks the overall shape of the object you're trying to examine. Precision refers to the level of detail or repeatability in measurements, while trustworthiness depends on validity, generalizability, and error control. Data can be measured to many significant figures, yet still be biased by systematic errors, calibration drift, or unaccounted confounders. True insight requires both precision and accuracy within known uncertainty bounds. A thermometer reading of 37.000 degrees Celsius may reflect sensor quantization rather than the patient's true body temperature. It is like a clock that displays hours, minutes, seconds, and milliseconds perfectly, but is set 2 hours ahead, technically precise, but fundamentally wrong. Overfitting occurs when a model learns random fluctuations in the training data rather than the underlying signal, giving spurious precision on that sample. Noise, random measurement errors, or environmental fluctuations can introduce patterns that an overzealous algorithm will treat as real. At fine scales, these artifacts dominate, so the most accurate fit actually encodes false structures. Fitting a high-degree polynomial to noisy sensor readings can interpolate every data point exactly but produce wild oscillations between them. It is like tracing every bump and crack in a road with your GPS so precisely that you end up with a map of potholes rather than the true route. As model complexity increases, variance rises, small changes in data cause large swings in predictions, while bias may decrease on training data but rise on new inputs. Finding the optimal balance is key. Too simple a model underfits, too complex a model overfits. At the tipping point, adding more parameters inflates apparent precision without improving real-world performance. In signal processing, adding too many adaptive filter taps fits every glitch in the noise, reducing predictive power. It is like using an overly long recipe with dozens of spices. The dish appears expertly nuanced but tastes muddled and inconsistent each time. Every instrument has finite resolution, response time, and calibration accuracy. Pushing measurements into its fringe regions amplifies systematic biases. Drift, thermal noise, and electronic interference often grow at the extremes of an instrument's range. Without careful characterization, readings that seem highly resolved can actually be dominated by these untracked errors. A voltmeter specified to measure down to microvolts may pick up ground loops and electromagnetic interference, swamping the true signal. It is like trying to weigh a feather on a bathroom scale designed for kilograms. You may read 0.001, but that's just the scale's noise floor. In complex systems, nonlinear interactions can produce apparent relationships that vanish when probed under slightly different conditions. High-precision datasets often reveal correlations that stem from unmodeled dependencies or random coincidences, not genuine causation. Such spurious correlations mislead analysts into overconfidence about system behavior. Economic indicators with 10 years of data may show a tight link between unrelated variables like ice cream sales and stock indices purely by chance. It is like noticing that every time you wear red socks, it rains, and concluding the socks cause the weather. Relying on over-precise but unverified data can lead to flawed theories, misguided policy, and costly engineering failures. Best practice demands reporting both detail and uncertainty, cross-validation with independent methods, and skepticism of extreme precision claims. Decision-makers should weigh the quality and context of data as heavily as its resolution. Overconfident climate model projections with narrow error bands may underestimate the true range of possible futures. It is like planning a road trip based solely on GPS ETA to the second, ignoring traffic jams and construction that the algorithm failed to account for. Validating high-precision results requires independent replication under varied conditions, a resource-intense process often neglected when data appear perfect. Small deviations in protocol, environment, or pre-processing can dramatically alter outcomes. Ensuring reproducibility demands transparency in methodology, sharing of raw data, and rigorous uncertainty analysis. Biomedical assays reporting minute concentration differences often fail validation in different labs due to slight reagent or instrument variations. It is like trying to replicate a complex cocktail recipe. Even a tiny change in garnish or glass shape can ruin the flavor profile. Emerging tools such as uncertainty quantification frameworks, ensemble modeling, and instrument self-calibration aim to align precision with reliability. Machine learning interpretability methods can flag overfitting and highlight when reported precision exceeds real information content. Cultivating a culture that prizes honest uncertainty communication will ensure that increasingly precise data truly advanced knowledge. In aerospace engineering, digital twins now incorporate sensor noise models and redundant systems to prevent false readings from triggering control errors. It is like upgrading from a single barometer to a network of weather stations that cross-check each other, providing not just precise readings but confidence ranges for forecasts.